To continue from the previous section, there are four basic ways in which you can toughen a ceramic by adding fibers. So the first method is by having the fibers interfere with the crack propagation. Suppose you have a crack passing through the middle of a block of material. Say for example you have a crack running through the middle of a room, and if you have trees all growing in the middle of that room, then that crack will find it very difficult to move from one corner to the other. So that is by having the presence of fibers to interfere with the crack propagation. The second one, so during that process, the crack will get deflected from one point to another. So the crack will have to move between the fibers in order to move from one point to another. Even though there could be a crack, the fibers themselves might be strong and may not let the whole component break and fail. So this process is called crack bridging. So the fibers will bridge the crack and help to keep the whole component together. The next one is, suppose you have the component in fatigue and there is a crack moving from one point to another and the fibers have still not failed. So they will start pulling and diffusing the crack and diffusing the energy of that crack. So that will also toughen the material. So this is basically the friction caused by the pulling out the fiber from the matrix, and that will also result in a higher toughness for the component. There are other variations of the toughening mechanisms, and all that is listed in a paper, a review paper, a couple of review papers written by a person by name Roy Rice. And I'll be posting that, or I'll be emailing that to you. And that is also an excellent paper to look at. Now, what is the biggest advantage with composites is that most of the time these are artificial materials. So you can somehow create a set of equations to determine what will be the properties of this component or this fab or this composite by adding two materials that are completely different from each other. And so this is different from the way you have alloys and things like that. So if you know the basic properties of the one phase and the basic properties of the second phase, if you bring them together, you really cannot predict what will be the properties of the alloy. You cannot. But in the case of composites, you can. That's the biggest advantage. So you don't have to make the actual composite and test it and test thousands and thousands of tensile test samples or shear test samples and things like that. You can predict those properties using a set of simple equations. And when you add two of these materials together, you have two ways of mixing them. You have two ways of determining those properties, and those sets of equations are called series and parallel mixing. So that is, there are a set of controlling parameters. I will come to that in the next few slides. So these equations are, for the parallel one, you can predict the stiffness of the composite by assuming that the modulus of the matrix times the volume fraction of the matrix plus the modulus of the uh, particles of the fibers and the volume fraction of the fibers. And if you have series, it's a slightly more complicated equation. The series mixing equation is a little bit more conservative type of equation. You don't get the same type of properties in the case of the composite as in the case of the parallel mixing mixing equations. So how do you come up with this equation? So this one is a definition or how it is derived. So what do you assume in the first case? That's called the isostrain condition. So you assume that the stress on the composite is the same as the stress on the fibers and the matrix, or the load is, and that the load is shared between the fibers and the matrix. So if you calculate the stress is equal to load over area. So that can be divided for the composite stress on the composite times area is equal to stress on the fibers times the area of the fibers plus stress on the matrix times area of the matrix. Since you have the same length of the fibers and the matrix, you can say that the volume fraction is shared between the fibers and the matrix, and the overall volume fraction is equal to 1. So you can say that, and also you can say that the strain on the composite is equal to the strain on the fiber is equal to the strain on the matrix. So you can derive that the stress on the composite times the strain on the composite is equal to the stress on the fibers times the volume fraction of the fibers divided by the stress on the strain on the fibers. So you can see the equation. So from that you derive what is called the rule of mixture for binary composites. So this is based on the isostrain condition, where you are assuming that the composite, the fibers and the matrix all undergo the same strain. Now, if the strain on the fiber or the strain on the matrix exceeds their failure strain, so one of them is going to fail and the other component will pick up the slack and adjust for the strain that is being exceeded on the other component. So from these above two equations, the load on each of the fiber and the matrix regions can be determined if the values of the elastic modulus of the fibers, the matrix, and the volume fraction of fibers and the matrix, and the load on the composite are known. So this is the most simple one. You also have the isostress condition, and you will have a slightly different type of definition and derivation. But the simplest one is the isostrain condition. Now, in order for a composite to fail, especially if the fibers are all aligned in one single direction, um, most of the time the fibers and the matrix are relatively brittle. They fracture in tension at very small strains after little or no detectable plastic deformation. So you can see that these are the failure strains for the different kinds of components, um, um, matrix ingredients. So the glass and the carbon and the Kevlar fibers, they all have pretty low failure strains. And even the resins have pretty low failure strains. So you can see that they are almost equal, but one of them most of the time has a higher strain to failure than the other component. But they don't have the same kind of strength, and one of them is stronger than the other, so they will hold the load for a longer period of time. This one describes the toughening mechanism of a composite, especially if there is fiber pullout. So if you have, most of the time, the fibers and the matrix are not the only ingredients in a composite. You also have what is called an interfacial region, which is different from the fiber and the matrix. So that has got different properties compared to both the fibers and the matrix. And when a crack grows in the matrix and approaches a fiber, most of the time it has to pass through that interface, and it has to shear that interface before the crack will enter the fiber or enter the matrix. If that interface is weak, it will fail in shear and the crack will turn and run along the side of the fiber until it finds a relatively weak spot on the fiber. Then it breaks and breaks at that point, and so on. And so this is how the a crack will move from one part of the composite to another. So what will happen? You have a crack that is running through, it hits an interface, and it travels along that interface till it finds a weak point in that fiber. Then it moves across at 90 degrees or at an angle, and then it goes to the next interface and moves across of the matrix, and so on. So in that process, the crack has to spend a lot of energy, and that causes the crack to slow down, which will increase the toughness of the composite. So you can see here there are so many fibers that have been pulled out of the matrix here in this picture. So these are called partially debonded fibers, and it has to absorb a tremendous amount of energy which will make this material break. Suppose this material were all matrix or all ceramic. What is there to stop that crack from progressing further? Nothing. But if you have these fibers, what happens is that that whole process of pull out alone will increase the amount of energy that the crack has to spend in order to move from one part of that composite to another. So composite materials, especially those with weak interfaces, are much tougher than their constituent materials. So this theory was originally discussed by a group of researchers from the National Physical Laboratory in England, and most of us have modified that theory in the last 15, 20, 30 years, but still the basic format of that theory remains the same. So they were the first ones to satisfactorily explain the phenomenon of multiple cracking. And they did what is called one-dimensional stress analysis, and they figured out what is the effect of the role of interface in load transfer from a soft constituent to a hard constituent. This process is called shear lag. So you can actually go in to different papers and find out what exactly is the shear lag theory. I'm not going to go too much in depth into that, but this is a theory that you will find in a lot of composite books, and even you might find that theory described and discussed in the Kishan Chawla book. So when this crack is progressing, so there is a average stiffness reduction in the composite, and that can be predicted by the different theories. So the biggest advantage you have in composites is that you can predict the properties, and you can predict the reduction in properties, and you can, suppose you know the external conditions, you can predict how this composite, based on the individual matrix and fiber properties, you can predict how this composite is going to behave, and how this composite is going to crack, or how this composite is going to fail. You can determine all that, and you can predict that. So you don't have to actually do the testing in order to predict what is going on in a composite. So the way they described and way they discussed it is in terms of, there are two types of composites. One is a brittle fiber in a ductile matrix, and the other one is a ductile fiber in a brittle matrix. And if you ask me, can you have a brittle fiber and a brittle matrix? Yes, you might be, but there is no point in doing that. So there is only the point if you have the matrix and the fibers have the opposite type of properties. And you can have either the ductile part or the brittle part, which will have the highest strength. And based on that, and based on the failure strengths, you can predict whether this material or the composite is going to have multiple failure, multiple fracture, or single fracture. So, if one of the two constituents of a fibrous composite breaks at a much lower elongation than the other, then the non-broken constituent is able to bear the load. So that means that if the matrix fails, the fiber is still there to bear the load. And you have to exceed the tensile strength of the fiber then in order for the whole component to break. So you can, especially if the elongation to failure for the different components are different, you can have either continued or multiple fracture of the more brittle phase until the specimen will break completely. So how does composite behavior occur? So you have two things. One is the ductile phase and one is the weaker phase. And the weaker phase is usually broken into a series of parallel cracks. And the work done in breaking the weaker phase may contribute to the work of fracture. And if the fibers are the stronger material, then you are going to spend a lot of energy in order for the crack to progress from one point of the component to another. And that will also contribute to the work of fracture. So let me stop here and I will continue in the next section.